And we're back to doing horizontal slicing for our areas. And once again, not replacing vertical slicing. Horizontal slicing is not our new replacement, like definite integral area was our replacement for Riemann sums. It's not like that, but just horizontal slicing provides another method of finding area using definite integrals that sometimes will be easier than vertical slicing. So it's cool to know how to do it when it's useful. And here are some example problems that you'll see. Horizontal slicing works very well for these problems, and this is the example problem video for the horizontal slices video, the intro part 1 video. This is the part 2 video. Okay, so here is our, well, first, here is the formula, with f of y being the right function, g of y being the left function, the whole right-left thing as it relates to top-bottom, because, I mean, this is, we're slicing horizontally instead of vertically, so it's different. That was all discussed in the intro video. But here we go. Y equals x squared, y equals 6 minus y equals 0. To find the area of the region in between those curves, and technically there's two regions, so the rightmost region is the region I'm talking about, and you will see how there actually are two regions when we graph this. Let's graph it. We're finding the area. So y equals x squared, the famous parabola, happy face parabola, like that. Not really, but there you go. You get the point. Y equals x squared. Y equals 6 minus y. What does that look like? That means that it's like somewhere like at 6, there's a y-intercept, and then it goes down. There's a slope, and I have a line function. So awesome. Like that, right? And so, that means the x-intercept ends up being 6, right? And that's about connecting the line, kind of connecting the line again. Okay, and this y-intercept's at 6, also. The x-intercept's also at 6, because this is y equals 6 minus y. So when you plug in 0 for y, you get what? Oh, well, that's a problem in here, actually. In here, that's not y equals 6 minus y. That is y equals 6 minus x, actually. Whoa, that was crazy. Y equals 6 minus x. For all you people who were confused, and even for the people who weren't. Y equals 6 minus x. And when you plug y in, not for, well, wait. When you plug y in, when you plug 0 in, not for, oh my gosh, not for x, but for y, what do you get? You get 6 for x. So yeah, the x-intercept is 6. That was the whole point. Y equals x squared, y equals 6 minus x, and y equals 0. The infamous y equals 0. Not really. The simple line doesn't get too much more simple than this. The green line, y equals 0. What color green did I just choose? I think it was this. Y equals 0. I want my colors to match for the line tool and for the marker tool. The same green color, but I think that's the same color. Okay, so the area we're trying to find is this awesome red region right here, in between y equals x squared and our two lines. Cool. Well, if we were to find, and it goes all the way in here until y equals x squared, until the origin, when y equals x squared equals 0, because because there is a point right here when the graph of y equals x squared touches the x-axis. But we're finding the region shaded in red. If you try to find this area utilizing the vertical slicing technique, you would run into a slight problem. The top curve changes. So at the start, the top curve is purple, and then the top curve is orange, and so you would have to like split it down the middle like that, or I mean it would be straight, like perpendicular to the x-axis, and so you have to have two definite integrals, which sucks. So it's a better idea to slice it horizontally. It actually would take less time. Fun, right? So if we were to slice it horizontally, we have our infinitesimally small horizontal slices, you know. Then, okay, what's the formula? The formula is up here. And there you go. Okay, so f of y is the right function, g of y is the left function. Okay, so f of y being the right function would be that orange curve. And g of y being the left function would be the purple curve. Okay, cool. So first, that's the right curve. The problem we have here is that it has to be in terms of y, because it's f of y, and this is in terms of x. So you have to get it in terms of x. So when you do that, right, this would be x equals 6 minus y. That's what your new curve is, your new right curve, in terms of y. And then your curve to the left, as I said, is the purple curve. That's also not in terms of y, so you have to get that in terms of y. So that means x equals the square root of y, right? So those are your two curves. Okay, fun, right? Now we can actually do this definite integral, right? Let's evaluate it. So the integral and our functions, the right curve minus the left curve, right? So right curve is 6 minus y, left curve is square root of y. So 6 minus y minus square root of y. 6 minus y minus square root of y. dy. Cool. Oh, we need to get our limits. We need to find out what our limits are going to be. The a and b, what are those going to be? Those have to be y coordinates. They have to be values of y. So what are those going to be? Well, the bottom y part of the curve is y equals 0. Right? That's a natural function that was given to us, y equals 0. And the top part of the function, I guess it'd be the highest the area goes is the intersection point between the orange curve and the purple curve. Y equals x squared, y equals 6 minus x. What is that intersection point? Set them equal to each other. X squared equals 6 minus x, which is x squared plus x minus 6 equals 0, right? And in the end, you find out that that has to be x equals 2. X equals 2. And so remember that you want y coordinates. So at x equals 2, the y coordinate would be, by just simply plugging in 2 into either of these equations, you find out the y coordinate is 4. And so that is your definite integral. And all you got to do now is just solve it. As simple as that. Making room for my definite integral taking process. Here's our integral, and actually, you know what, I'm just going to do it up here. I'm going to make a lot of room. I'm just going to do it up here. Okay, so, realize, by the way, that there are two regions here, right? There are two regions. There is another region, namely this region. But as I said, I meant I said the rightmost region, so I meant the one that I actually shaded in red. So that was the region I was referring to, not the region that I just shaded in black. Okay, so when we try to evaluate this integral, okay, first of all, this is 0 to 4, 6 minus y minus the square root of y, which we should write as y over y to the half dy. Okay, now you can evaluate this doing the antiderivative. 6y minus y squared, well, okay, half y squared, right? Half y squared minus 2 over 3, y to the 3 over 2, evaluated from 4 to 0. Cool. And now when we simplify this, when you plug in 0, everything becomes 0. So you don't even have to worry about that that lower limit. Just forget about it. All you got to worry about is the upper limit. So just plug in the upper limit. That's all you got to do. 6 times 4 minus a half times 4 squared minus 2 over 3, 4 to the 3 halves equals 24 minus 16 over 2, which is 8, minus 4 to the 3 halves. 4 to the 3 halves is the square root of 4 cubed. Square root of 4 is 2. 2 cubed is 8, or 16 over 3. 8 times 2 over 3 is 16 over 3. Okay. 24 minus 8 is 16, minus 16 over 3. 32 over 3 when you find common denominators and do the difference, which is the answer. 32 over 3. And so that is how you would find the area of this region using horizontal slicing. And, oh, what happened to the formula? We don't have the formula anymore, which if you want it, oh, one slide too far. Here is the next question, and as I said, if you want the formula for the area, a to b f of y minus g of y dy, y, f of y being the rightmost curve, g of y being the leftmost curve. And I'm going to ask you to do this, of course, and pause the video and come back when you have an answer, or simply if you just don't know how to do it. Okay, so finding the area of x equals y plus 2 squared and x equals 0 and x equals 4, the region bounded by those curves. Graph it. Yes, let's graph it. So we got something crazy. This is an interesting curve, which you probably noticed if you did it, because this is at least a region we're concerned with, is beneath the x-axis. Surprise, surprise, surprise. So the graph looks something like this. And that's x equals, well, I'll just put a line underneath it. And then your other graph is x equals 0. X equals 0. I will draw in blue. X equals 0 is simply the y-axis. Yay, right? And then we have x equals 4, which I will draw in yet another green. and x equals 4 is like somewhere like over here or something, right? I don't know exactly in particular, but that would be 4. Also, that is 4. These are all x equals 4. And so the area we're trying to find then obviously becomes the area in between, right? But the real question is, okay, how are we going to find the area when this is for horizontal splicing? Vertical splicing would be really weird, actually. And so if I were doing this and I had a choice of vertical splicing or horizontal splicing, I would choose horizontal splicing, which is what we're supposed to do here. So these are problems that are horizontal splicing works very well for. And so when we look at our formula, what's our right curve? F of y. Our right curve is the green curve. So that is x equals 0. No, sorry, not x equals 0. X equals 4. X equals 4. And my left curve is the light green curve. X equals y squared. X equals y plus 2 squared. And so our integral is like, starts off with x equals 4, minus, let's see, y plus 2 squared dy, right? And then a to b are our limits. So what actually are those limits? Remember, they have to be y coordinates. So they give us limits in terms of x equals 0 and x equals 4, but we have to get y coordinate limits. So instead of our, dark blue and dark green lines, we need x coordinate versions. So, y coordinate versions. So our y coordinate version, one would be up there, and then another one would be up there. Right? Obviously, this one's going to be 0. And then the one beneath, what is that going to be? It's the intersection of x equals y plus 2 squared and x equals 4. The intersection of both of them. So, set them equal to each other, and you find out square root y plus 2 and 4 equals y. What did I just do? No, I did not. Did I just seriously make that mistake? That is 0. Y equals 0 at the first intersection point, which is this one, right? And then when you square root it, though, you could have a plus or minus 2, technically, right? So the idea then is that you could actually, you could get a negative 4, if you, if it's a plus or minus from the square root. And so that is negative, what am I doing? That is negative 4. Okay, so those are our limits. Negative 4 and 0. Those are the limits for the integral. And so then, evaluating the integral, well, I could do that, but I'm not going to do that because the video is already long, and you should know how to evaluate these integrals by now. And so, if you were to evaluate the integral, you would get 32 over 3, actually the same answer as we got for the previous example. And that would be your answer. And so, this is the area for in between these curves. And it's as simple as that for horizontal splicing. Sometimes you do horizontal slicing, sometimes you do vertical slicing. Whatever is best at that given moment. Okay, there you go.